Okay, so we can start the day with an overview of what's new in the latest version of Ceph, and as by the end, a little bit about what's coming in the following version. To show where we are in history, the last release was called Luminous. That's the 12.x.x release. Next one will be called Mimic. You probably noticed if you're not very familiar that these are alphabetically increasing, and they happen all also to be species of cephalopod. You might also notice that the left-hand side of this diagram, we have Jewel and Luminous, which are long-term supported releases. Kraken was not. But on the right-hand side of the diagram, everything seems to be a long-term release. And the reason for that is that we have the new release cadence. We used to do releases every 6 months, and every other release was a long-term supported release. This had some downsides. A year was a long time to wait for a fully supported long-term release. And when we explained to people that the intermediate releases like Kraken were not LTS, but they were stable, that was sort of a strange halfway situation. In practice, people ended up using them anyway. So now we release every 9 months. Everything is stable. Everything gets backports, but only for the next 2 releases, which means 18 months. So of course you can talk to your vendor, whoever you're paying for support and so on, about releasing your support for longer than that. But this is what you get from the upstream Ceph community. Stable release every 9 months with backports for the next 2 releases. So this is not really an intro to Ceph talk, but for the benefit of anyone who's not very familiar, I just want to quickly run over some terminology. So this is the classic Ceph cluster diagram, in which there's a client at the top of the slide, and then the cluster consists of OSVs, which are the services that sit on top of the disk drive, monitors, which are the central coordinators of the cluster, and there are also some MPS's metadata servers in there, which are used if you're running the Ceph file system. And Ceph gives you 3 ways to use it. You have Cephs, RBD, and RGW. RBD is the disk-like layer, what you typically use for something like OpenStack Simba. RGW provides an S3 compatible interface, and Cephs is a distributed file system, similar to must-have cluster or GKS. They all sit on top of the same underlying object storage layer, which is called Rails. So, moving on to what's new in Luminous, that's a Luminous squid, after which the release is named. We have a new backing store for USDs. It's called BlueStore. BlueStore was introduced in Kraken, but it's only fully supported and stable as of Luminous. Unlike the previous file store backend, we're not consuming a local file system like XFS. We're using the block devices directly. We're also embedding a library called RocksDB to manage the metadata about the data that we're storing on the drive. This gives us a huge speed improvement because previously we were doing full data journaling. Everything we were writing to this was getting written twice. Now we're not doing that anymore because we have more control in the way the data is stored. That enables us to implement the Ceph transactions without the need for the full journaling. So this is an easy 2 times speed up if you're simply running on a single hard disk drive. The situation is a little bit more nuanced if you were using an SSD for your journaling, but in the best case, you can double speed your Ceph cluster. For example, at home I have a Ceph cluster which is all hard disk drives, and it's twice as fast now, so that's great. Because we're not journaling all the data anymore, the journals are now smaller. BlueStore still lets you store them on separate devices, typically an NVMe device, and you can fit more of them on, and you're consuming less bandwidth on your journal devices now that the journals are smaller. And a couple of bonus features, which are pretty important to some people. We have data checksums to improve your data integrity, and we also have inline compression available at the block layer. So here are some charts. These are from during the development of BlueStore, so they actually have several different BlueStore variants. But the key thing from this chart is that the file store line, the blue line, is well below the other BlueStore lines in terms of throughput. This is random write throughput. Here's random read-write throughput. Again, the blue file store line is below the BlueStore lines. And an even bigger difference here, I'll come on to erasure coding in some more detail in a second, but on an erasure-coded workload, where we're doing a RAID-like storage of data instead of replication, we difference is even greater because erasure coding stresses the OSDs much more than replication does. So you see a much bigger improvement for BlueStore versus FileStore. The yellow and the green lines here are BlueStore. I didn't make these graphs, but if I had, I would have made the BlueStore lines blue and FileStore lines the other color. So next up, erasure coding. Ceph has had the ability to do erasure coding storage for a number of releases, but previously, if you wanted to use it with RBD or Ceph, you had to have a caching tier in front of it, a replicated tier. That was quite a big drawback. It was complex, it added extra resource requirements. So now we can use erasure coded tools directly from RBD or Ceph. You may also see this referred to as EC overrides, since the underlying mechanism that's needed to support this is the ability to not only write an erasure coded object, but to overwrite it and modify it in place where what device or file system requires. So this does require BlueStore. If you ran it on FileStore, you would find the performance was very bad. So this is a BlueStore only feature. Erasure coding, of course, gives you a big increase in efficiency compared to replication in the use of your storage. The downside is that small writes are slower with erasure coding than with replication because we're having to operate on a full EC stripe at a time, much like your RAID controller is doing if you have a traditional controller. Large writes, though, are faster simply because we're writing fewer bytes to disk. So consider for each workload what the right answer is. Replication for best latency, small writes, and so on. Or erasure coding if you want to get the absolute maximum storage out of your underlying drives, and especially if you've got large objects. In Luminous, the Ceph Manager daemon, which was added in Kraken, becomes a mandatory part of the system. So this is something that supplements what the monitors do and used to do. So they've taken some of the functionality out of the monitor daemon and put it in a separate daemon, and at the same time added in some new stuff. So the manager daemon has a Python interface that enables you to load and run various different modules that extend the Ceph cluster and give it interfaces to the outside world. For example, integration with Fabrics, Prometheus, InfluxDB, and a REST API. And this is completely extensible. Anything you can think that you want to do to have your Ceph cluster communicate its monitoring status with the outside world, you can implement as one of these Python plugins. There's a little performance improvement here as well for the monitors because they're having to do a little bit less work. Previously, the monitors were receiving a message about the status of their replacement group every few seconds. That's now being handed off to the manager. It's taking care of that instead. And this was some really good testing at CERN, thanks to the guys at CERN for their big bang cluster testing with this. And we now have a web dashboard. In the Luminous release, this is a fairly simple thing. That's just read-only, it's just showing you the status of your system. That's shipped as part of Ceph Manager. You don't have to install anything separate. It's like Ceph Manager module enable dashboard, and this will start listening on one of your local ports. The output of some of the commands has been cleaned up, made it easier to use. There was a sort of focus on usability throughout the Luminous release. So that's what Ceph status looked like in Kraken. That's what it looks like in Luminous, cleaned up. The health reporting used to be a little bit too verbose. You would get a separate health message for each ad status that a placement group was in. That's also been cleaned up, so you get a single message that summarizes that, tells you what's important, which is how many of your objects are degraded, and also distinguishes in this message between degraded data redundancy and degraded data availability. Previously, you had to know what all of the individual PG states meant to understand that. The cluster log, which is what you saw when you typed Ceph-W, used to be extremely verbose. It was dumping the status of the placement group map, which summarizes the whole system every 5 seconds. And if you look to the log, that's generally what you can see. It's been cleaned up to have much more meaningful messages. So we're now emitting messages to the cluster log when significant events happen, such as the system going from a healthy state to a degraded state, an OSD going down, an OSD coming back up, that kind of thing. It's kind of what the cluster log should always have been like, but for a long time it was dominated by those PG space messages. In further performance improvements, we have a new class called async messenger in the code. So this is kind of an internal detail, but it affects you if you care about performance and resource consumption. All of the Ceph services use a class called the messenger to do their network I/O. And they used to use one called the simple messenger, which created a separate thread for each peer that it was talking to. If you had to run the ulimit command to adjust the number of permitted threads in the Ceph services, this was why, because it was creating one for each peer. OSDs kind of talk to all their peer OSDs, clients talk to all the OSDs holding objects that they want to load, so both clients and Ceph servers had a very large number of connections. So the replacement, async messenger, is event-driven and uses a fixed size thread pool. So you no longer have the overall number of threads going up with the size of your cluster, which is a big improvement. This is also bringing some new backend possibilities. So there's a new RDMA backend, which is not very heavily tested, but appears to work by all accounts. And there's also a DPDK backend. So DPDK is Intel's framework for user space packet processing. And integrating this with Ceph is going to be very important to take advantage of next generation storage devices like NVMe devices. Because otherwise you could find that your network, the rate at which you can send packets over the network could actually become a bottleneck to the rate at which you can access the local devices, because the new devices are so much faster than traditional storage devices. So watch that space for DPDK. There's been improvement in the way the data is balanced across OSDs. Previously, this was always done statistically, which meant that if you had a large number of cluster groups, you would end up with a reasonably even layout of data. But there were cases where that didn't work so well, and especially if you had a smaller cluster or a smaller number of placement groups, you could end up with a few % more data on one OSD than the other, which would mean your effective point at which your cluster became full was a few % too soon. So there's a new internal mechanism in the way that we handle the crush algorithm, the data placement, that enables us to, on a per pool level, control the weighting of where it puts the data on different OSDs. There's also a mechanism that enables us to explicitly override the crush algorithm for particular placement groups. So if you have that one last little PG that just won't go to where you want it, there's now a way to tweak it to make it go to the place that gives you the best balance. That would be quite a heavy thing to do by hand. So there's also a new Ceph Manager module that does it for you called Balancer. And the Balancer module will examine the balance of the data in your cluster and use a statistical technique to optimize the data layout and then gradually move the data from one OSD to another. And there are even more robust improvements that there isn't time to go into in a lot of detail. So crush device classes enable you to put your pools on SSDs versus hard disk drives in a much simpler way without having to custom edit your crush map. Disk replacement is more efficient and simpler. We have a new command called Ceph OSD new that takes an ID argument and lets you essentially steal the ID of a failed drive rather than having to create a new one and delete the old one. There's a setting called requirement at client that you can set to have the cluster refuse to talk to clients older than a certain version. That makes the upgrade simpler. So when you enable a new feature that requires recent clients, rather than having clients just fail if they're too old, it handles it elegantly. Configuration options now have metadata in Ceph. If you're building a user interface or any tools that interact with Ceph and you'd like to show somebody the documentation string for a config option, that's there now. Clients handle stuck PGs or objects much more efficiently than they used to. They used to have to block their requests on the OSD. The OSD would have to hold the request in memory, and that could cause an issue on cluster that's having a lot of problems. The OSD is now able to tell the clients to back off, call me back later. The EIO handling, so the handling of IO errors on physical devices, has been improved. The OSDs now have a path where they will handle an EIO by attempting to repair and recover from one of their peers, rather than just reporting the issue to the administrator to try and themselves. And there are performance improvements everywhere, especially in placement group peering. So what happens where you have a failure and the PGs need to get back into a good state. And also where the OSDs fail, previously we used to wait for a timeout. Now they can proactively detect that. It's a very long list, and it's kind of amazing how much stuff has gone into Luminous over the period of 6 to 9 months. And I should also emphasize that there are many different individuals and companies contributing to this. So when I say we, I mean the Ceph community as a whole, contributing all of these great features and improvements. That was the underlying Rails layer. Now I'll talk a little bit about each of the application layers and the improvements that have gone in that. So CephFS has long had, in theory, the ability to run multiple metadata servers, but it was a little unstable, and for Luminous it has been made stable, tested, bug fixed, and it works well now. So you have scale-out metadata performance. You're no longer limited for a workload with a large number of clients, especially if you have small files, by the throughput of a single MDS daemon. You can deploy as many of them as you want. Well, up to 128, but that's too many for any real use case. To make the best use of that, we have a feature called subtree pinning that enables you to explicitly associate a directory in the file system with a physical MDS daemon. It's not always necessary because the cluster will dynamically move the data around, the metadata around the cluster. But it means that if you already know at the start of your workload that I have 10 clients working in 10 equally busy directories and I have 10 MDS daemons, I don't have to rely on the auto balancing to work that out. I can just pin things where I want them to get the best possible metadata performance. It also enables you to isolate certain clients if you really want to. CephFS large directory support is stable. So if you have millions of entries in a directory for some reason, then the underlying mechanism where CephFS will fragment that directory into many pieces is enabled by default in Luminous. So if you create a directory with many files, it should just work. And as with the rest, many bugs fixed, many tests added. Moving on to RGW. RGW has an NFS gateway component, which enables you to access it like an NFS share for the purpose of importing data. It's not a general purpose NFS file system, please don't use it as one. But that now supports NFS version 4 and NFS version 3. There was previously a scale issue in RGW where if you had too many objects in a particular bucket, the bucket index would become too big, performance would suffer. The bucket index objects are now dynamically sharded, so that problem is fixed. RGW has inline compression now as well. Obviously, you probably don't want to use that in addition to the restore compression, but one or the other depending on your workload. The S3 encryption API is now supported by RGW. And we have a really neat new metadata search feature. So RGW has the ability to synchronize asynchronously between data centers. And that same protocol that we use for syncing between data centers can now also be plugged into